The topic of my talk is spin dynamics in sucrose-derived luminescent carbon dot-silica nanocomposites. This work was done in a collaboration with Lashkaryov Institute of Semiconductor Physics. The synthesis of the sample and photoluminescence characterization was, thank you, was done there. So my talk will be organized as following. First will be some short introduction about the subject, then I will proceed to motivation, and then materials and method, and an experimental part. First the photoluminescence characterization, then electron spin resonance measurements data, and then I will end in conclusion. So carbon dots now, it's a very modern topic, and it's a new type of carbon-based nano-sized material. They consist of discrete nano-sized quasi-spherical particles with mean diameter less than 10 nanometers. They have very interesting properties such as adjustable photoluminescence. They are chemically inactive. They have highly degree of solubility in water, and what is important, easy and low cost production, and also they are non-toxic. They usually contain a mixture of sp3 and sp2 hybridized carbon atoms and shows an amorphous character. One of the type of carbon dots is a carbon quantum dots. They are new zero-dimensional nanomaterials. They have discrete quantized energy levels and the different density of states. Now this topic also attracts very much attention. You see the publication now rises on this topic because they have very interesting properties such as a tunable photoluminescence, and it allows them to be used as modern effective universal fluorophores. Specific electronic properties of carbon quantum dots, they are mainly are related by quantum mechanical effects, and as a result, such parameters as an energy gap, band gap age position, and the density of states become size dependent in those materials. The reduction of carbon quantum dot size leads to modification of the density of states from usually band structure to the discrete energy levels, and in the end we end up with the LUMO and HOMO levels, so we will have a molecular electronic structure. Another interesting effect there is the optical quantum size effect that appears when the size of carbon dots approaches the Bohr radius. So what's happening here? The photoluminescence peak, it shifts from blue to red range with increase of the particle size, and at the same time the band gap narrows. So in the last years, light emitting materials that show broad band visible photoluminescence takes a lot of attention because they can be applied in modern optoelectronics and artificial lighting system. But the problem is that most modern materials that emit daylight, they contain impurities of heavy metals, and of course it leads to undesirable effects on our environment. One of the possible solution is the application of silica carbon nanocomposites because they're environmentally friendly. They show photoluminescence in the near ultraviolet and visible range, and the spectral properties of the light emitted by them can be controlled by variation of the synthesis condition. It is known that carbon dots are the dominant radiative centers in those materials, and therefore the study of the physical properties that depends on the synthesis condition now a very interesting task in the point of view of future application of this material in modern optoelectronic devices and also in bioimaging. So why we use fumed silica as a matrix for incorporation of carbon dots? Because it promotes the dispersion, it protects the luminescence from so-called quenching effects that usually caused by the environment that contains water and oxygen. Carbon dots, silica, nanocomposites, they show very interesting photoluminescence properties. The emission spectrum covers the broad spectrum from green to yellow range, and it differs from usual blue fluorescence that observed for carbon dots. And also the wavelengths of the photoluminescence of carbon dot silica nanocomposites depends on the excitation wavelengths. So let us proceed to materials and methods. Now all methods for obtaining the carbon dots, they are divided into two main approaches. One is so-called bottom-up and another is a top-down. In bottom-up approach, the assembling of nanostructures is carried out from the individual atoms and molecules. And one of these bottom-up methods is the fabrication of carbon dots based on carbohydrates. Carbohydrates as a precursors for the carbon dots synthesis is very interesting because they are widespreading, easily available, have very good heterogeneity, high solubility in the water, low carbonization temperature, and what is also very important, low cost and low toxicity. In our work, the carbon dot silica nanocomposites were prepared by infiltration of humid silica matrix. It was a powder with a mean diameter of 10 to 12 nanometer by sucrose water solution as a carbon source. Different concentration of sucrose solution from 800 millimole per gram to 8 millimole per gram were used, and different annealing temperature were applied from 300 to 400 Celsius. It was done with the aim to investigate the effect of carbon incorporation in our samples. As a method of investigation, the electron spin resonance or electron paramagnetic resonance was chosen. It's a resonant absorption of microwave radiation by paramagnetic systems in the presence of an applied magnetic field, and it's based on the well-known Zeeman effect when the energy level splits in the presence of the magnetic field. And this method is now widely and effectively used as a non-destructive method for investigation of magnetic and electronic properties of defects and impurities that appear in modern carbon nanomaterials. The ECR spectra were measured in continuous wave mode at X-band frequency range on Bruker Alexis E580 pictometer in the wide temperature range from helium to room temperatures using helium flow cryostat. Prior to ECR measurements, the photoluminescence characterization was done. Our samples show a strong white light emission that covers the spectral range between near ultraviolet and near infrared region and has a maximum intensity at about 450 nanometer. The annealing of our samples lead to the shift of the photoluminescence spectrum in the green-orange range and also lead to decay of the integrated intensity of photoluminescence spectrum with the increase of carbon content. And also we have seen a green-yellow emission in the samples that had a higher carbon content after thermal treatment. So let us proceed to ECR data. Before thermal annealing, we have not seen any ECR signals in our samples. The reason that the spin concentration of paramagnetic centers is very low there, and it is beyond the detection limit of our pictometer. After thermal annealing, a single ECR line was detected in the samples with sucrose concentration higher than 8 millimole per gram. So on this figure, there is a dependence of spin concentration on sucrose concentration in our samples. You can see that the increase of sucrose concentration and increase of annealing temperature leads to increase of the spin concentration in our samples. On the next slide, there is a temperature dependence of ECR spectrum that was measured from room temperature down to helium temperature. It was done in two sets of the samples. First set had a sucrose concentration 400 millimole per gram, another was 800 millimole per gram, and different annealing temperature were used, 300 and 400 Celsius. We have found that our spectrum represent a single line that has isotropic G factor, and this line was attributed to paramagnetic center with electron spin 1/2. You can see that this line has a temperature-dependent line shape, intensity, resonance field position, and a line width. So all of these effects we will discuss in the next part. So first is a line shape. You can see there is a asymmetry in our line that observed very clear in the figure on the left down. So what causes this asymmetry? Usually in ECR we see a classical Lorentzian and Gaussian line shape where this to A to B ratio is equal to 1, so they are the same, but it can be that there will be the case when A to B ratio will be higher than 1. We will have an asymmetry, and it caused by an appearance of so-called Dyssonian line shape. It appears in the sample where there are some conductivity appear, and the reason is a skin effect there. So we can say that there are some conductivity in our sample. On the next figures, there are examples of fitting of experimental spectra with a Dyssonian line shape. You see there is a very good agreement, and we have done such a fitting for each temperature point for all of the set of the samples, and as a result we have drawn the temperature dependence of the total spin accessibility in our samples. It was done using double integration of ECR line that is proportional to total spin accessibility. So we have drawn the direct spin accessibility temperature dependence and the reverse one. So it was found that our temperature dependence has two terms. The first one is a Pauli-like term. It comes, so it's temperature independent, and it tells us that there are some conduction electrons in our spin system. This second term is a Curie-Weiss term. It's a temperature dependent, and it appears due to localized spins in our system. And the first term governs the temperature dependence at higher temperatures, and the second at low temperature. So we can suppose that there is a coupling between conduction and localized electrons in our system. And indeed, when we have built a temperature dependence of resonance magnetic field position, it shows a typical behavior for the case when there is a strong exchange coupling in the spin system, and it's a coupling between localized and non-localized electrons. We have described it theoretically, and in this equation it's important two parameters. It's a resonance magnetic field position for localized and non-localized electrons, and using the resonance condition for ECR, we have found the G factors for localized and non-localized electrons in our system. So here is a table where we put the values of Curie-Weiss temperature and those G factors that we found using the fitting of experimental data. The Curie-Weiss temperature was found to have a minus sign, so we can tell there is a weak antiferromagnetic coupling that occurs in the localized spin system. And the G factor for non-localized electrons was found to be equal to 20045 in the samples analyzed as 300 Celsius, and it should correspond to oxygen-centered carbon-related radical, and the G factor 20037 was found for the samples analyzed at 400 Celsius, and it corresponds to carbon-related radical with an oxygen atom nearby. The G factor for localized electrons was found, and using the literature data, it was attributed to carbon dots. So in our samples, there is a coupling between carbon-related radicals and carbon dots. Another interesting effect is the temperature dependence of the ECR single line width. So the such temperature dependence is typical for so-called motional narrowing effect. It appears due to the variation of the spin-spin relaxation time with the change of the spin motional energy. So what's happening in our spin system? At higher temperature, spins move faster, and it allows them to spend less time near the phasing center. As a result, the coupling between investigating spins and the phasing center, it increases, it leads to the longer T2 values, and as a result, our ECR line narrows. At low temperatures, the non-localized electrons, they start to move slowly due to interaction with localized electrons. It leads to shorter T2 time, and our line broadens. We have described our experimental data with a theory. It was described by the Anderson-Weiss spin exchange narrowing model. And what is interesting in this equation is the tau, its average time each spin spent between allocation, and n is the number of hops up to the moment when phase covariance disappears. So in this table, you see the parameters of fitting of this equation with experimental data, and we have found that highest n value and shortest tau time was found in the sample that was infiltrated with highest concentration of sucrose and analyzed at 300 Celsius. So those samples should show the highest conductivity. And indeed, if we compare this AB ratio, this asymmetry ratio for the Dyssonian line shape, it was found to be the highest one in those samples with sucrose concentration of 800 millimole and analyzed at 300 Celsius, and this A to B ratio is proportional to conductivity. So we can suppose that carbon dot size in our case increases with increase of the sucrose concentration. At the same time, carbon dot's band gap reduces, and it causes the conductivity of carbon dots silica nanocomposites, and the previously observed shift of the photoluminescence and further quenching effect of photoluminescence in our samples should be caused by the quantum size effect. So the main conclusion of our work. In carbon dots silica nanocomposites that were obtained by infiltration of a sucrose solution, carbon dots and carbon-containing oxygen bond radicals are formed, and they should be responsible for the photoluminescence in those samples. The samples that were obtained by infiltration of sucrose solution with a low concentration show an intense photoluminescence, and they can be potentially be used to make fluorophores and light-emitting diodes. In its turn, the samples obtained by infiltration of sucrose solution with a higher concentration, they show higher electrical conductivity, and we suppose it can be potentially be used for manufacture of optoelectronic devices, for example, photocells. Thank you for your attention.